So in the case of like the epidemiological model, like we encode the number of infected people, the number of recovered, the number of susceptible. And then we have a law of motion. Basically, the law of motion says, given the current state, what my state's gonna look like in the next time period. So if you have like 50 susceptible people today, how many susceptible people will I have tomorrow? How many infected people will I have tomorrow? And this law of motion is that encoded with the function f. So there's a theorem in mathematics called the Picard-Lindenlof theorem that says that there is a unique solution under certain regularity conditions of the law of motion f, for which there's a unique solution of for u. So if you look at this equation, we know that we only know how the function changes as a function of time. What we would like to know is what we like to have is a function u that's only a function of time that will tell us, okay, at time 100, what does my state looks like? So at time like 50, what does it look like? Only given only given my initial conditions, so u0 at a given time t0. That might sound like that might seem quite incredible that that given a law of motion you only have one trajectory allowed. But if we think about what the law of motion represents, it just represents like infinitesimal steps that run from a given initial time to like the end of time. So if you start with if you write our function ut as a function that starts at time 0, so ut0, and we add to it like all the infinitesimal steps that are represented by du dt equals fu. So all the infinitesimal steps are added with this integral here. So I'm saying like I'm summing over all the steps from t0 to tet. In this case, I'm trying to find the function u for tt. So like if we approximate this, so if you say that ut0 is our initial condition, so equals to u0, we can approximate this as a sum of like of all the observations that we have. So let's say we measure our data every 10 seconds. So we can approximate this function as like, so for 10 seconds, we know that the function changes according to a certain rate. So for 10 seconds, I'm going to assume that we're accumulating so much. And then for the next 10 seconds, I will assume that we're accumulating so much, and so on and so forth. So it's like an iterative process. So this is basically why our function has a single trajectory. It's like if we know how much we're gonna move forward, and there's only one way to move forward, then of course like there's only one trajectory that is allowed by that law of motion. So we cannot, unfortunately, like this doesn't represent a solution of our system, because as you can see, like our what we're looking for, that's the function ut. Here is defined as an expression that is also a function of ut. So it's a transcendental equation, and we need actually to solve it so that we have ut on one side and everything else on the other side. In many cases, it's not possible to find an analytical solution. So it's a solution that's only a function of time and of the initial conditions. And in that case, we solve it by using numerical integration. So it's basically by following this process of like adding every step and look at how it changes. So we're gonna start. So we're gonna move on to Jupyter again, and now that I've defined what's the initial value problem, I will then show you like how we solve for this problem in Julia. So we're gonna now work mostly with the Lotka-Volterra problem. So I will remind you what this differential equation system looks like. So there are two species in the environment. So there's a species 1, that's the fox, the rabbit. And there's species 2, that is the fox. So there's the species 1, the rabbit, is born at a certain natural rate alpha, and then dies according to the rate that is predated by the fox. So this rate beta, and rabbits die according to how many foxes are there and how many rabbits are there. So if there's a lot of foxes, a lot of rabbits, then they will be more likely to die because it's easier to find them. And then on the other hand, the fox is born according to the rate at which they can feed themselves and reproduce. So delta U1, U2, and then they die of natural rate gamma U2. So for solving differential equations in Julia, you use the package called differential equations, and the packs and the plots for plotting. So differential equations package is a very big package. It's actually subdivided in many packages, and if you go to the documentation, it's very extensive. And then there's many tutorials, and I recommend that if you are interested in learning more about it, that you go through the tutorials. So we're gonna be following for this part of the workshop. We're basically gonna go through this tutorial, so showing you how it works, and then and applying that to the Lotka-Volterra. And I think here they apply it to slightly different systems. So a good way of learning about differential systems is to adopt a model of your choice. So if you go back to if you go back here, and so you just choose one of those models, and then you can try yourself like to replicate the concepts that I'm teaching today. Okay, so this has been started, and then the first step then is to define our function. So our function is our law of motion. We want to define a function, so LV for Lotka-Volterra, which is gonna modify the inputs. So that's why we have the bank here. Again, the bank is just a convention; it's not a requirement. So what are we gonna modify? So du is our infinitesimal step. So if you look here, du is this one, du over dt. So this is one of the inputs. So again, we are iterating through this function. So just to find the solution numerically. So like we start at time 0, then we're gonna find what the function look like at time 1, then at time 2, time 3, and so on and so forth. Like you can have this idea in the back of your mind. This is the basic. This is basically how like one method for solving the differential equation work, and then after I will talk about slightly different methods. Okay. So you define, so du is the first input, and then u is the state of the current system, is the current state of the system, and then p are the parameters. So p is a vector which contains the parameters alpha, beta, delta, and gamma. And finally, t is the time is the time that we are evaluating the function. So to define a law of motion in the package, in the differential equations package, we need to define a function that has this signature. So has exactly. So you always have to define the du, u, p, and t in this order. So as I said, p is the parameters. They hold all the Greek letters here. So we can for like readability's sake, we can allocate each one of them to a Greek letter. So alpha, beta, delta, and gamma are equal to p. and then we have the infinitesimal change will be equal to exactly the equation. So alpha times u1 minus beta times u1 times u2. And what are we doing here? We're modifying the vector du. Du was holding like maybe the change from the previous state. And now we're gonna modify this vector and we're gonna allocate the change for the current state. So notice that we never use the input t, because this model is what's called non-autonomous. So the parameters don't depend on t. So there are models for which the law of motion also depends on the time variable. So like it could be the case that your parameters change depending on the time. And this you can find more about that in one of the tutorials here. So I forgot which variable was, but I can show you after. So we're gonna follow the same. We're gonna follow we're gonna solve the model that's in Wikipedia. So like this model here. So if you ever wanna go back, we solving this simple example here. So this model goes from, it starts with a population of equal rabbits and equal fox. So there's one fox, one rabbit. You can think of it as 1,000 fox, 1,000 rabbits, or 100, whatever. Doesn't really, the magnitude doesn't really matter. And then we're gonna run our model for a period from time 0 to time 50. And again, this doesn't really, the time that you evaluate your function is up to you. Like usually a differential equation, how differential equations work is like there's a transition period for which like you go from your initial state to like Bayesian of attraction, no, to an attractor. Sorry, you start you have an initial condition which goes to a certain attractor. An attractor is like a set for where your function is gonna be contained. So the Bayesian of attraction is all the sets of initial conditions allowed, and then your state is gonna travel through this attractor. That's where your function is gonna remain. So it's gonna be clear when I show the graphs. And then our parameters. So I called it LV for logical Volterra and the scar P for parameters. So our true parameters will be like 1.1. So the rabbits grow. So grows at a rate of 10%. Whereas like the fox they die at a rate of 40%. And then the rabbits are hunted by the fox at a rate of 40, and then the fox they grow at a rate of 4.1. So as we know, the rabbits reproduce much faster. So we have the alpha is higher than the fox. Okay, so once we define our law of motion, so LV, we define our initial condition. We define the period that we want to compute the solution for, and then we define our parameters. Now we can solve it. So we want to find out the function u. So we say we initiate a ordinary ODE problem. We pass the law of motion. We pass in the initial condition, the period, and the parameters. And then the second command, solve, will basically solve the function. So it was very fast. If you're trying your computer, it might be a bit slow because the first time you run it, it compiles, but then after that, it goes pretty fast. So I run it again, and I'm just gonna show you like what I get. So just a second. So first, like what the problem looks like. It's so once you define the problem, it just basically returns you like a problem statement. And it shows you like the initial condition and the time span. So and then the solution basically gives you like the time for which the solution was evaluated, so the t here, and then for each time period it gives you like the state. So of course this you might ask like, oh, but which time will it return? So this is defined by the algorithm that finds the solution, but you can control that. So we will talk about that a little bit later. So so again, like let's go back to the algorithm. So I was talking about the about computing the trajectory using small increments. So this is basically what's called the Euler method. So 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 this method basically like we rewrite what is exactly the law, what is exactly the change. So it's basically like so you have a state at period t plus delta t. So a state one period ahead, and then we have the current state, so ut, and then we divide this by the amount of time that elapses between two states. And that should be equal to our law of motion. So if delta t is very small, this is basically the definition of a derivative. And because of our definition for the law of motion, like this should be equal to the law of motion. So if I rewrite the step ahead state ut plus delta t will be equal to the current state, so ut, plus delta t fut. So basically, I multiplied both sides by delta t, and then I added ut on both sides, and then I end up with the expression. So basically, what we are doing when we call solve in a very simplistic way is to compute basically this expression. So for each of those time periods that I find the solution for, I'm computing it iteratively. But as I described here, this is not computationally feasible because it might require a very large number of iterations, and depending on how the system changes and all that, we might want to be a bit smarter about how we compute these iterations. In particular, like some ODE systems are what we say stiff. So there are two kind of like ways that the function is changing. So there's a short run rate of change. So in the short run, the function like oscillates a lot. There's a lot of abrupt changes. But in the long run, there's like a clear trend of how the function is evolving. So the function could be growing very smoothly in the long run. So what happens if you use this iterative system, the Euler method, is that like we might compute a value. So we might be here, and then we compute the next value, and then we might end up outside of the function. Even though we're trying to approximate it with a very small step, because the derivative is very high at that location, we end up like overshooting. And then once we overshoot, we're not going to be able to go back to the original function. So that's why it's difficult to find solutions for ODs, because even though we can have this mental model in our head that the solution is just basically like a series of steps, what really matters when you're computing a solution is like how big a step you want to take, and will I still be in the same will I still be navigating the function, or will I overshoot? So there are methods that tries to be clever about how to solve the system. So maybe they will look a few steps ahead, and then they will try to back out to walk backwards to kind of like find a midway. There are systems that will like compute like small step, like compute a large step and a small step, and then add them like as a with certain weights. And then I invite you to like check the documentation for like reading, if you're interested in like reading more about all the different solvers. So that's why we call them. solvers for finding numerical solutions of ordinary differential equations. So in our case, we're using this one of the most common one. So the default is to use one of the most common solvers called TCT5. So it stands for TC Torres 5 for Ranjakuta, which are basically the people who developed this method. And this method is basically doesn't look in the future. So like it computes a certain number of steps ahead and adds them like with a certain weight, such that like to ensure like that we are like clever about how we want to move forward. For methods that are stiff, like this one, like represented in the picture, we actually want to look into the future and walk backwards and make sure that we meet halfway. And these methods for stiff equations are identified here. So are described here. Like so if you think your system is stiff, and it's easy to find out when you have numerical integration problems. And Julia will tell you is to look into the documentation and look for which ones are for stiff problems. So here there's a description of like the different solvers, so which ones are recommended and all that. So I'm not going to go into a lot of details here because it's beyond the scope of the workshop, but I just wanted to give you a pointer. So let's explore what the solution gives you. So up to this point, do you have any questions? Like maybe something was unclear. Is the mental model for differential equations clear in your mind? Okay then. So let's continue. So the solution contains, so the solution, remember, the solution is will be obtained by calling solve on the problem. And the solution will contain, so again, here I solve it again to kind of show the solution. So I start with my problem, and then I say which solver I want. So in this case, I want the default one, so the Ranjakuta 4-5. Then I'm gonna tell you what's that type of tolerance I'm willing to accept. So the absolute error and then the relative error. So basically, the absolute tolerance and the relative tolerance are described in the page for the solvers. But basically, say like how far off from the actual function I'm willing to be. So when I'm computing the steps, so like how much further from the actual function I'm willing to accept. And then like usually E minus 8, like E minus 8 is a bit higher, like not the highest, but it's the default. And then like if you have some solvers that are very slow, maybe you can. So the lower the tolerance, the faster it solves, but the more likely it will not find the correct solution. On the higher the tolerance, the slower it will take, but more likely that it will find a solution. All right. So we can take the solution and plot it straight away. So we just call the command plot. So I pass a label for it. So I define the label as a vector. Notice that we separate the labels with just a space. So this is like a row matrix. And then here the size is just like for presentation. So I don't want it to be very big. So I put 400. So you could just call it, if you're just doing some experimentation, just call it straight with the solution, and you plot to like a bit bigger without the nice labels. All right then. So as you can see, the solution is sort of cyclical. So an increase in the rabbit population is followed by an increase in the fox, which then causes the rabbit population to decrease. So apart from looking at the solution as a function of time, we might want to know like, okay, so if my rabbit population increases, what's going to happen to the fox population? So if you think about the problem, like the problem can be described as a system for which you have the value of the state at the value of some variables at the current time, then you would like to know, like, okay, what are the other variables going to look like? And so, because all the variables change according to time, and then the state of each variable has an impact on the other, so we can in fact compute the partial derivative, so how one state influences the other, and basically then we can so we can basically plot this expression using the same command plot. So we plot the solution, and then we'll say, oh, we want to look at the variables 1 and 2. So the variable 1 is the rabbit, and variable 2 is the fox. And then if you write variable 0 is time. So I could have like the 0 and 2. I think I have it down there. So yeah. So the plot interface is very flexible, and it actually like the package defined recipes. So when you call the plot with the output from the solution, it already knows how to plot it. So here you see like the cyclical behavior. So when the rabbits are increasing, the fox increase slightly, and then it reaches a point of no return, and then the fox eats all the rabbits, and then they start eating other rabbits, and then they increase a lot, but the rabbits decrease, and then it goes down very abruptly. So we can also find what's the size of the solution. So you see the solution here is very smoothly, but we might we can actually plot it in terms of like so the solution is not a line, like it's just like a bunch of points. So you might want to plot as so you can say type, and then scatter. So let's see. Okay, so well, basically it's almost the same, but there's a lots of them. But you could but basically like you can you basically have like 573 point evaluations. So like we have 50. Our time goes from 0 to 50, and we have like our function is evaluated at 573 different time steps. So it's basically like for each second, we get 10 evaluations more or less, and then the chew stands for the number of variables. So we can also retrieve, like, let's say the state at time 10. So here you go. So and then we can also so the state at step 10 is not the time period. It's just like the 10th evaluation. So if you want to know what time was at time 10, we just do T10, and then it will give us the time. So it's at 4.87. And then finally, like we can compute the solution for an arbitrary step. So if instead of we use the brackets, we use the round parentheses, so it means we're calling a function. So the solution is also a function, and then it will compute the solution at time 47.5. So don't try to compute a solution very far out from your observed period, because the solution is basically like a linear interpolation. So you might not get the solution you're expecting. So if you like to find a solution for like time 100, then when you call solve, when you set up the problem, you wanna set up the t-span for the period you wanna find a solution for. All right, then. And then we of course we can change the parameters of our model to understand how the solution changes. So here I set up a loop. So for each initial condition here, so I have one initial condition we have like, I don't know how many, like maybe 10 or initial conditions, and then I will remake my problem. So I set up my problem up there, and now I can remake it. So I take the problem and I redefine the initial condition. So the initial condition that I want now comes from the loop, and then I compute a new solution. So and then I gonna produce a scatter plot. So as opposed to the line plot that I had. So yeah, remake is part of the OD library. So it's available. In my personal experience, I find that it doesn't really matter if you remake or if you set up the problem again. I haven't seen a lot of like difference, and I think a lot of the time they just remake the problem. Like I just reuse this OD pro. I just call from OD problem, but I'm sure there's some maybe gains in terms of memory. And so what I want to show here is like then you can plot everything, and then you can add. So every time you use a plot bank here, what I'm saying is that like, so plot, when I call plot, so when I say plot size equals 10, plot gives me an object. So if I say what's type of it's a plot, and then basically when if I return the plot, this is an object, and it just prints the objects like the same way that if I type like this, it will return a string. So every time I do a bank on the plot, so plot, I can plot a function. Let's say a function that goes from x to x squared. So if I put a bank, it will add the plot to the current active object. So that is computing this. So I can pass any function, and I need to plot. So it plots there, but you cannot see because it's very small. So what I can do is I can show the plot, still too small. So what I can do, I can maybe increase the size. So I can say size equals maybe 400. And there you go. So every time you put a bank, that's the nice thing about plotting in Julia, is that like it's very flexible. You can add things to the plot. The plot's just an object. You just keep adding stuff and resizing and adjusting it. And then after you end up with a nice plot. I find it very, very convenient. So in any case, you can find the documentation of plots. Let me close some windows here. So okay, so what you wanna look for when you're like customizing your plot is this part here. So attributes. So if you go to attributes, you're actually gonna see like all the different types of attributes you can use, like the x label, x limits, the ticks, and everything. And then if you look at each individual attributes or series attributes, it will actually show you like everything you can use. And in the beginning, it can be a bit overwhelming, but after you get used to it, it's like I find it quite convenient. I just look at the table, like let's say I'm gonna change the line color, so I'm basically type find color, and then I find it here, and then I see, okay, color of the line. We take the value, and then I read, and then I can change. All right, then. So when I do scatter bank, so scatter is just a convenient function for calling something like plots. It's just basically a way of saying plots type scatter. So instead of typing this, it's basically saying scatter. And then so I type the fox and rabbit population with the label. Then the marker size equals 1, and then the marker width is 0. So the bank just means, so it's a convention, and developers, when they use bank, they're just saying like we're gonna modify the objects that we are passing. So for the plot function, we are modifying the current plot. So as once you, as long as you don't start a new plot, so you always start a new plot when you call function without a bank. So if you do like this, you start a new plot. Then every time after that you use a bank, you're basically modifying the current active plot. So that's what I'm doing here. So I started a plot, and then I want to keep adding new things to this plot. So I started. So like the way that I explained, it only works for plots, of course, but in general, like here, I put a bank when I define this function, the Lotka-Volterra function. I put a bank. What I'm saying, what I mean here is that I'm modifying the vector du. So every time, like in Julia, that people put a bank, it just say is just saying like it's just a contract between the developer and the user to say the developer is going to modify any of the arguments in the function. Usually, it's the first one. So the user should be aware of that. So it's very convenient because a lot of times you don't want to copy objects, you just want to mutate the objects. Until the bank, it's an indication that I'm mutating. So for instance, if I define an array like 3, 4, 2, 4, and then I call the function push. There's no push without bank. So the push, the function push takes the array, and then you can push a new object. So let's say 3. So it's gonna modify the array foo. And there we go. So now if I look at the array, foo, it has a 3 there. So yeah, it's just some syntactic sugar for helping to establish an agreement between the developer and the user. All right, so now I'm plotting every function. So I start with the one in the middle, and then I go increasing in this direction. So I'm trying to show here in this plot is that every solution here is cyclical, except for the solution defined by this array here. Now this parameter here is this set of initial conditions is very particular because it basically defines the initial condition for which that is an equilibrium. So the function, so we start at the solution, and this solution is basically unstable. So any small perturbation from this initial condition will generate a cycle. But if I start my problem exactly in that location, I'm always going to be there because the law of motion means that I'm now moving basically, and that's why I decided to plot it. So if you go to the wiki page, they actually have a discussion of that, and then you can see here the stability. They discuss the stability of the fixed point. Here they discuss how to find this fixed point, and the fixed point is given by the parameters of the function. So here, so yeah, feel free to read it. Always reach if you're interested in the topic and you wanna continue learning, and you can always send me an email after the workshop. I mean, it'll be good to collaborate and talk more about it. So yeah. So okay, so I've defined exactly. So I've shown you how to solve a problem. So up to this point, we've done nothing but solving an ordinary system of differential equations. We haven't even looked at data, but in real life, we're not giving the problem, we're giving the data. So how can we go from the data to the problem? So let's say like the data comes in this form. So at time 0, you have 1 rabbit, 1 fox. So time 0.34, you have 1.3 rabbits, 0.9 fox. And then it's basically a time series. So it basically, in most circumstances, when you're dealing with data from systems of ordinary equation, you're dealing with time series. So if you come from economics, maybe you used to use AR models, the models of like autocorrelation models and regressions. This is one way of modeling time series from economics. Now, when you're coming from physics, your system changes in a continuous fashion, and then it's easier, it's better to describe the system in terms of differential equations. So there's so maybe like I'm just trying to say like the time series can come from different places, but but it's always gonna look like the same, like the time and the states. So how do we find then the solution for the, so if you get the data like this, like it might not be obvious, like how do you actually like fit the data to this, you know, because like I know that the problem changes according to law of motion. So, but I'm given the data in terms of states. So how do I fit that? Like, since you have to, there seems to be a discrepancy. So one way, a simple approach, like you might think, okay, well, wait a second, I can just compute the difference. So like I started. So if I have a list, I will just take the first difference between, let's say, 0.0 and 0.034. The time step, the time difference, the duration is 0.34. And then if you compute if you subtract 1 from 1.3, you end up 0.3. So you see an increase in the rabbits. And then you see, on the other hand, a decrease in the number of fox. So then we could take this, and then we could fit this model to a linear regression. So, and then you could then obtain the law of motion, like as simple as that. So I guess like this is the way that it's usually done in economics. If you heard about the auto regressive models. So this would be like a typical approach in economics, to take the first difference and then compute this linear regression. So here it's in terms of the lag, but you could also write this regression in terms of the difference. But this is not a good approach, because basically like of the problem that I mentioned before with the stiffness and in how things change and how the system might be evolving, a finite difference might not really be representative, might not be a good approximation of the derivative of the system. Especially this gets aggravated when the data is very sparse. So like instead of measuring the system every second, you might measure the system every 100 seconds, and then there might be a lot of things happening in between. So instead of computing the finite difference, like a classical approach like that works is like you start with you initialize a model. So in this case, you hypothesize that your model looks like the logical Volterra model. Okay, that's the first step. Then you start, initialize that model with arbitrary parameters. So you could start the model with any of these initial conditions that, you can start the model with any set of parameters that you can imagine. So here, I started the model with this set of parameters, but you could start with anything you would like. Okay, then, okay, that's the first step. Then the second step, when you try to find a solution for that model, given the proposed parameters. Then the third step, you compute the cost. You find the difference between the solution that you computed. So the solution is this one, which basically gives you the state of the system at every time step. And you compute the cost, so the difference between the solution and the observed time points in the data. So you have the observed time points in the data, and then you have the solution for an arbitrary parameter set. And then the first step is that you modify the parameters in the direction that would cause the biggest reduction in cost. So basically doing gradient descent. And because like we're dealing with so our solver is basically is basically a way of like taking finite differences and finding the solution through gradient descent. So you can imagine like that I could modify, I could take the derivative of these methods to find like the direction that would cause the biggest change and reduce my cost. So I haven't reproduced any of this computation here, but this is basically the idea. And maybe later on in the workshop, there's a section that goes more deep into that. And then finally, I repeat the steps from 2 to 4, like until like I basically converge. So until my cost is very small. Okay, so that's the basic algorithm. So let's look at how it would look, how we would do that using data. Like so we just generate some fake data. So let's imagine that we have an observation span that goes from 0 to 10. So in our solution above, we had from 0 to 50, and then we generate data for we generate a time series for the of 30 steps, and so I end up with this this model here. So if I plot it, so I'm just generating fake data from the problem above. Sorry, I have to. So, oh, sorry. So this is our more fake data. So here I had to transpose the vector because the plotting library expects a column vector, not a row vector. So basically like our data. So we started with the solution. So I started with the solution, and then I say, oh, I'm imagine that like I end up with the data set that goes from 0 to 10, and then I only observe like 30 points. So this is how like my fake data looks like, and that's what I call like observation. So in order to go through this little iterative algorithm, I'm gonna use 2 libraries. So the first one is called the diff equisensitivity. So this is for computing sensitivities and to gradient descent. And then the second one is the equiflux. So actually, like this library is like wrappers for the machine learning library Julia. So the Flux is the neural network library of Julia. But we can also basically use these libraries also to compute gradients and all that. And that's what we're gonna do here. So first we have to tell then Julia how to predict observations. So first thing, like you can ignore the first line for now. I'm gonna go back to it in the second part of the afternoon. So we're basically saying like solve the problem. So I give an input. I give a parameter set p, and then I say solve this problem with the initial conditions that I know because I have the data. With this parameter I'm testing, and then I'm just gonna decrease the tolerance so to make the computation faster. And then the sensitivity algorithm you can just think of like as a way of taking a derivative. So this is how I predict my function using the given any arbitrary parameter sets p. And this basically corresponds to the second line here, find the solution. Okay, and second, I want to compute the loss. So what's the loss is basically I have my observations. And then like I want to save my solution only at the observation steps. So here I define observation steps as the time periods from 0 to 10 at the step of 0.34. So that came from I know that from the data. So because the observations, my predictions, I compute the predictions for every single time step of my observation. I can compute the loss. So these are just 2 functions that are one is predicting, the other is for computing the loss. So there's step number 2 and 3. And then finally, I use the machine learning, the SML train method from Flux. So I'm basically passing the loss function here, and then the algorithm is basically iterating through the steps 2 to 4. So it's finding the solution, computing the cost, then modify the parameters by doing gradient descent, and then go back to find a new solution, computing the new cost. And then it basically goes over and over until like it's, so I say how many iterations at once. And so it goes for 300 times, and then it finds the solution. So that might take a little bit of time on your computer. Oh, so what's the return? So yeah, maybe I didn't say, but in Julia, if you define a function like any function, foo x, and then the last line, let's say 1. This will be the return. This will be the return of the function. So I don't need to say return 1. It will just return the last line of the function. So if I go bar, oh sorry. So if I go bar 2, it just returns 1. So here I'm returning this array because it is the last line of the function. So that's why I return an array. So when I say predict with the certain with the parameter p, I'm basically just computing the pointwise difference between 2 vectors. So that's why I'm using the broadcasting. And then the sum function allows you to pass. So you could pass any function here. It could be like square root or anything. So we take the square root for all the elements of the vector, and then we'll sum them. So as you see, like just doing that, because I know I know the exact model. So again, I'm just basically solving the problem. And then see here, I didn't use the remake. I didn't use remake when I'm doing the prediction. I'm gonna explain about the sense algorithm later on. So just hang on with the question, and it will be clear later on. So here I didn't also need to remake the algorithm, the problem. I basically can just pass out the new parameters, and basically everything new I can pass to the solve. So that's another reason why I don't tend to use the remake. It's there, but I just pass everything new to the solve. So as you can see, like the original parameters are 1.1, 0.4. So I can recover it pretty close. And then I can plot the data and the solution. And then basically I end up with the, you see like the solution is behind, is a line, and then the observation is the points. So here I basically recover the function exactly how it is, but the cost, well, not the cost, like the trade-off is that like I needed to know the exact form of the law of motion. So what do we do if we don't know how the law of motion looks like? So that's what we're gonna cover after the break. So we're gonna talk about the neuro OG. So maybe before we progress, like, do you have any questions? So have you been able to run the notebook? Has it worked? All right, I guess then, well, I guess everybody's doing fine then. So we take a 5 minutes break and then we come back at 2:10. Is that okay? All right. Yeah, SMI train is gradient descent. That's right. Okay. Yeah, then I think you can check the. can check the documentation. There is you can just type here and try. If you want to learn a little bit more about it, so it's here. And then if you click source here, you can find the algorithm. Yeah, so I think like it just optimize the algorithm for working with the OD problems and all the differential problems that they define in the library. But otherwise, it's just simple. You can define your own if you want to. Like I played around before, but they just have like a routine that seems to be more stable and work better with the differential equations. But you can see here in the screen is just like you basically like computing the gradients, and then you use the K optimization function, which is basically like how you compute the loss. And then there is and then when you say galactics optimum solve is you're basically doing gradient descent use Adam, if you're familiar with Adam. And then after it does the Adam, it takes the same number of iterations and does a BFGS. So I don't know, just from experience from the developers, this seems to be a good approach to gradient descent using ordinary differential equation solvers. Yeah. Yeah, that's correct. Yeah, you can compute the hash. That's that's part of the. I think that that's so when you do the forward diff gradient here, I think that behind the scenes. So I'm gonna talk about the sense algorithm later, which is basically like how we compute the gradients. Yeah. So let me just go and get some water, and then come back at 2:12. So because I'm really thirsty. right, so back. Any questions that you might have? Okay, so I'm gonna continue now with the neurology part. So I guess that so our workshop kind of like culminates in the neurology. That's I guess where you're probably most interested, and I hope that I build up well until now. So the basic question is like so if you're giving a time series and you don't know anything about the model that generated the time series, like how can we recover the system that gave rise to the data? And if you believe that the system comes from that the system was comes from a differential equation was generated by differential equations, then we can use neurology to do that. And that actually is much more broad than you might think about. So let's review the initial value problem. So as I mentioned to you before, like the initial value problem is basically defined as giving a law of motion. So how the states change with time, and is given by a function f. And this function actually can be anything, like as long as it satisfies some properties that I'm probably gonna talk. I'm gonna talk maybe at the end of the workshop. As long as it satisfies some smooth properties, this function can be anything. So why not a neural network? So neural network is basically the mother of all functions. So you can think of it as a surrogate model, or you can think as just like a function approximator. It's just a function that approximates any functions given this right set of parameters. So, and then the number of parameters depends on the depth of the neural network and the width. And so like I'm gonna rewrite my law of motion. Instead of saying like the law of motion is equals to f, I'm just gonna say it's a neural network. In this section of the workshop, we will try to then fit our data to this network. So what's a neural network for those who are maybe not so familiar with it? And I'm gonna maybe review it from the perspective of OD. So as we can remember, like a neural network is basically like a function that approximates other functions in a certain way. So how does it do that? So you can in the most basic one, so is the fully connected network, and then it can be composed of many layers that look exactly like that, or it can just be this one layer. So the fully connected layer starts with an input layer, so that's U, and then you multiply by certain weights. So every arrow here corresponds to a weight, and that will map it to certain variables. So that's the hidden layer, and then you're gonna take a function. So if you look here at the formula, so W0 would be the weights. So I'm basically saying there are two inputs variables. So that, and then there are 1, 2, 3, 4 hidden layers. So basically I need that. So at the end of the day, I have 1, 2, 3, 4, 5, 6 weights. So basically like my matrix is it's 3 by 2. Sorry, 4 by 2. Here the picture doesn't depict all the errors. So you have a 4 by 2 matrix that corresponds to the weights plus a certain bias. So we can think about that we basically like we have a bias, like so more or less where our hidden layer should be, and then we add into it certain weights. So we are increasing or decreasing the bias according to our input factor. But then if there was just that, we would have basically a linear model. So we add the nonlinear activation function. So it just says it's just a way of like so only after the output of this expression reaches a certain level, we will output a value, or we will bound the values of that this expression between certain values. So the linear activation function could be something like a tan-h function. So so if you would like to know how it looks like, oh shit, sorry. So you can actually use Judo. So you can say tan-h, and then you just plot it really. So here you go. So this is how it looks like. So if it's so the function is either 0 or -1, either -1 or 1. So when the function is very close to 0, it can be some number in between. But this changes very fast. And then in most cases, if the output from our input, if our expression here, the W0 U plus B, is very high, then we'll bound this to 1. Otherwise, we'll bound it to -1. Other functions is the ReLU. I'm not sure if the ReLU is available. So, well, it's not here, but you can just write it like it's the minimum between x and 0. I think that's the so that no, sorry, the max. Sorry. So this is the ReLU, so the rectified linear unit function. So if a function is negative, it's 0, and then otherwise it's linear. So there's many different types of activation functions. Just show you some of the most popular. And you can learn more if you go to Wikipedia. I'm sure you can read all about it. So because like there's the leaky ReLU that's like has some nice properties and all that. But anyway, it's not the goal of the workshop. And then we end up with the output layer, which is basically like you multiply by another matrix of weights to obtain our output. So this function is basically like it could be thought as a complicated black box, but basically like it have an input, you go through all this pipeline, and then you have an output, and the output basically can be anything, like our function maps. This big expression here could map to a simple function like x or x squared, or it could be an even more complicated function. So among the class of neural networks, one network that really changed the field is the deep residual network. So it was published in this paper, Hey et al. 2006, and I think was one of the most published papers in the history of machine learning. Though the history is not, I guess, that long, especially the recent one. So basically, what we're doing is like, so we start with the inputs. So here x, we've been using u, but here is x. So there are two paths that we can take. So we can either go right, and then we just map x to the identity. So we just end up with the same inputs. And then the other path is the left path, and then we're basically saying that like x goes through some neural network, something that looks like this. But in the case of image, it's a convolution network, a convolution layer. And then at the end of the day, after it goes through this network, I sum. So this can be expressed as f. So f is the neural network plus x, which is the identity. So the nice thing about this function is that it basically like allows us to approximate the input, allows us to approximate the identity function. So if you're using traditional neural networks, like it's be very difficult using gradient in the sense to map the inputs to the outputs, because you have basically to change out the weights in a certain way, and because there's the non-linearity, it would be very difficult to find the identity function. So the idea here is like, and if you look at the bias here, what we're basically saying is like there's some weights and we add to the bias. So let's imagine that our input is actually the bias, and we want to add like some nonlinear change to it. So we're basically saying like, okay, I start with my input, and then I'm gonna move one step forward, and I'm gonna add some sort of some infinitesimal change. But now I'm talking the same languages as the language of differential equations, like, because in fact what I'm saying is that like the residual layer, which is this layer F here, is equal to the difference between the layer that came before and the layer that and the current layer. So XL plus 1 is the current layer minus the layer that came before. So I'm basically saying that my input changes according to a law of motion that's defined by a neural network. So I'm basically, again, describing an ODE. So in the case of ResNet, like all the steps are, which is depicted here in this picture, which might be a bit small. So I'm just gonna open here in Google. So in the case of ResNet, you have like you have all the skip connections. So like you start with the inputs, so you can ignore the first layer. Start with the input, and then you jump, you skip, and then you add some residue. So X plus the residue. So this is the first change. This is the first addition. Then another addition, another one, another one, another one, another one, another one. So we basically like we're basically computing the solution for an ordinary differential equation. The main difference between the ResNet and other functions we defined before is that every step here of ResNet, you have a different set of weights. So when I'm looking at the first jump, you're gonna have like a certain set of weights. Then when I'm looking at the second jump, you have a different set of weights. So we want to optimize the function, the weights, every single time step. We have a different type of we have a different set of weights. Whereas, as I mentioned before, like with ODEs, the parameters of the function they are basically fixed. So in this case, W is always the same. You cannot change. So the main difference. So what about like instead of like changing the weights every time we skip, we keep the same weights, and then we treat this as an ordinary system of equations. And basically what I'm saying is that like if you think about an image, we start with an image, so the picture of a bird, the picture of a ball, and that image lives in a certain space. So that space is maybe like is the space of a matrix. So like if the image is 256 by 256, so that's the state. And then I'm gonna move through this space such that like such that I wanna reach like I wanna move through the space and reach a new location where the different classes of images are separated very easily. Because after they go through this through this motion, like I will have like birds in one part of my space, and then you have like giraffes in another part. So in a sense, like is the idea of like is the sensitivity to initial conditions. So when I'm classifying images, I'm basically saying like every attractor is a class. So every attractor is a ball, is a bird, and so depending on where I start, so my basing of attraction, I'm gonna navigate it to one attractor. That's my class. And ResNet, in a nutshell, we can think that it's basically doing that. Is like pushing the function through this trajectory, and then I'm gonna land exactly in the class that I am interested in. Right. So maybe like the, does it make sense? Like the way to think about ResNet and the way to think about neuro ODs. So basically, neuro ODs are basically this, like it's basically like a neural network layer interpreted as a law of motion. And that's why like it was used initially with images, but actually you can use with any other in any other field. So is that clear? Would you like to add anything? All right then. So let's see how to get things done in Julia then. So okay, so again, like let's remind about the two parameters of the model. So in the previous part of the course, we said that the two parameters, the initial condition is 1, 1, and the two parameters are this ones here. Okay, and then we derived the solution for the system, and then we also like sampled a few data points, and we call this our fake data. So now we're gonna use the Flux package. So the package for defining neural networks in Julia to define a neural network layer. So we start with the fast chain. Fast chain is just a way of concatenating different layers, and then we go with fast dense, and then fast dense. So just basically replicating the first layer here that I expect. So Flux actually defines Flux doesn't define fast chain, fast in fast dense. It's the diff equi package that does. And so these are just wrappers for the actual implementation in Flux, and gives you some extra functionality. But you could build everything using Flux. So if I go to the source code here, so fast dense is just like it's just a layer. You have the input, the output, you have the activation function, and then you have some initial parameters in the bias. So if I open the Flux documentation, and then you can also search for the dense. So Flux has a dense layer, and then I can go to source code again, and then yeah, again, like the layer has the weights, the bias, and then the sigma. So the difference is that like fast has the fast layer. I think I missed it. Okay, so if you compare both, like this one has weights, so the difference maybe is the out and the in. I'm sure it is there for efficiency purpose. Okay, so I'm saying that the input has 2 dimensions. So we have fox and rabbits. The output has 50 dimensions. So the hidden layer here would be 50 nodes like this. And then I use the activation function is the 10H. Then after it has gone through that, I use an input like will be 50. So this will be 50 nodes, and then I will map back to 2. And notice that I didn't pass an activation function here. So that means I'm using the identity. So exactly this expression here. Okay. so now that I've defined my neural network, of course I can call it. This is the neural network. I could call it with anything. No, I cannot. I think I cannot call it. Oh, I think I can. So like there, like so I have to pass the parameters, I think. So okay. Okay, I think kind of forgot. So but okay, maybe I'll figure out. I'm doing something probably not quite right, but in any case, so I can define the neural network. So once I define the neural network, I define the ODE. So the law of motion is basically you start with the state u, so our parameters p, and the time. So then I can call it. So it's just the same way I did it now, but somehow it doesn't. It's not working. So maybe if I call like this, maybe okay. Okay, maybe I need. Yeah. Also, sorry. Yeah, like I'm embarrassing myself. Yeah. So I need to call the. So like I'll call it just a little bit later. I need to define the parameter. So because the parameters now changed, no. So it's actually a good thing that I made the mistake. So the thing is like we know the true function. The true function has as parameters LVP. But now we're dealing with a neural network. So the neural network has what 50 times 2 times 50 times 2 parameters. So actually it's a vector. So there is this function here called initial parameters. Basically initialize the parameters of the neural network. And basically gives me a vector of 252 elements. So actually like this model has 252 parameters. So when I call this function with the parameters, it then computes like the next step. So thanks to you for helping me with that. Okay. Okay, maybe I have to pass as a vector, I think. Okay, there you go. So apologies for this confusion, and I think again it was good that I did it so like to see how that we're really doing two different things. So yeah, so like so it's a very good thing that as you says that like we can be very specific about the parameters. And then I'm just saying initial parameters, but in fact like if I just did like I could have any parameters really, like I could like be like 1 to 252, you know. I think that would work. You see, compute something like makes no sense, but you could use like, or you could have like a repeat 0 like 252 times. Okay, the repeat function also is I guess I have to do like this. Yeah, so I could have 0, then of course the output is I could have 1. Anyway, you got the idea. So so what I'm doing here is that like now I don't know what the model looks like. I hypothesize that I can approximate with a neural network, and then I will define my law of motion as, so I started my neural network, and I say my law of motion is the following: is a neural network, and I pass the state u and the parameters, which are the parameters of the neural network. And then you notice here, if you compare with the Lotz-Volterra equation, like the Lotz-Volterra equation had this input du, but actually like the OD problem allows you also to define a function LV that doesn't take du, only takes u, p, and t, and then you then return the differential. So in that case, like it would look something like this. So you would have to start a new vector of like, let's say, float 32, and then and then 2, and then you basically like do this, and then you return du. And so basically here you would so I just show you like you can so here you can do that. So you're basically just allocating the memory every time that you're basically allocating the memory every time you run the problem. Okay. So again, like and then I find the solution. So the main difference is that like here I'm computing the change and allocating to a new vector. So when I use this way, and then as you can see, find the solution. And when I'm using with the bank, and I have to add the input du, I'm basically like modifying the vector in place. So this form is much more memory efficient. This form is like it's more memory hungry, I guess. But these are true. Both are possible. So that's why here I am I'm defining my OD function like that. And what I'm doing here is because like basically there's no reason to allocate the output of the neural network to the vector, I guess. I'm just returning it straight away. And then if you ask me which one should you do, like, to be honest, I wouldn't be able to tell. Maybe the other way is more efficient. So you would do something like this. So then you would allocate so you would allocate it. So that also works. So I guess it's might be that this way is less efficient, and you probably have to use the benchmark tool set to figure out which one's better. Okay, so now I define my problem, and then I again define my problem and OD the initial parameter, the initial values, and then I use the observation span that I computed before. So it goes from 0 to 10. So okay, so up to this point, so when we solve the problem, the traditional problem before, we use the SciML train, and it allows you to define a callback. The callback basically can print anything you want, can plot. So if you're using VS Code, you can change your plot as you go, as you descend through the as you do the gradient descent. So the callback takes the following inputs. So it takes a solution. So the solution, it takes the observations, takes the problem, basically you can take anything you want. There is if you go to the documentation, and then you can read more about the callback. So like sometimes like you can also not take anything. So okay, so here what I'm doing is that like I define the callback as the following. Okay, sorry. So the callback, I stepped back. So I define a callback that returns a function. So my callback, so every time a defect of Flux expects that your function takes a parameter, in that and then it takes the L, and then it also can, and then it can also like take this keyword argument do plots, I think. Okay, so basically, like, then I define a wrapper for this function, so to make it easy to like create callbacks, so that I don't need to redefine callbacks. And this is a place where probably if I knew more about macros, that I would benefit from defining a macro instead of defining this closure here. So when I wrote the notebook, it was a month ago or so, I was not so familiar with macros. Now I know more about it. Maybe I would write a macro. In any case, so the callback is basically doing that. When I say it plots, it will plot the function. Otherwise, it will just like keep a counter, and then it will push the losses to an array that I have initiated before. And then I will print the current loss every time for every 100 iterations of the function. So yeah, so here again, like so here I start the loss vector of losses. So because the gradient descent can work on GPUs, so I just use float 32 for everything. On my computer I don't have GPU, so it doesn't matter. But like it's just like it's just a habit, I guess. And then I get a new callback function. So this is the true solution, the observations and everything. And then I initialize the parameters. So I call the function initial parameters that I showed before. And then I just plot the result. So as you can see, like I can solve I can solve this problem with the random set of initial parameters, and what I got basically is a nonsense function. So the correct solution is the cyclical solution we're familiar with, and what I got is basically like something that grows exponentially. So here's like the initial parameters 252. Okay, so I think it's like okay. Then now I have to tell Julia how to compute the prediction. So like before, I would say so. Then I have my neural network problem. I use the Range-Kuta method. I use the initial parameters from the data. The parameters here are the neural network parameters. Here they pass as an input to the function. Then I will save at every observation steps that I have available. So it's just like a range. And then I use a slightly higher tolerance. Before I was using -4, here I'm using -6. And then I'll use a different sensitivity algorithm. So this time is the interpolating adjoint. So that's why I'd like to maybe make talk a little bit about the sensitivity algorithms. Let's see. Okay, yeah. So did I talk? Okay. So basically, like sensitivity algorithm is a way of like computing derivatives. I had some pointers before. Here. So like a sensitivity algorithm is a way of like computing the sensitivity of our solution to the parameters. That's why it's called sensitivity algorithm. But in other words, it's a way of computing the derivative of our solution to the parameters of the function. So there are two methods, like none each other, two methods of doing that. One method is the forward differential sensitivity, and this method is basically computing the Hessian, as somebody mentioned before. We basically like taking the the derivative of the law of motion with respect to the parameters. And then we're seeing how the solution will be affected by it. And the force sensitivity is usually expensive. I'm not gonna get too much detail, but if you wanna know more about it, I recommend the course here. This one, and then in particular the lecture forward mode, so lecture 8. So we're just gonna open here because it has some nice pictures. Okay, excellent. So actually, like the force sensitivity basically computing the derivative as we know about it. So we take the function, we compute the derivative analytically, and we represent it in terms of function, and then we take the solution, and then we put that in our function, and then we compute, and then we obtain the derivative. So that's what the forward diff sensitivity is doing. It's a more complicated way of doing this. So here, function. When I was talking about function, I showed an example of that. So here, so for diff sensitivity is a wrapper for taking derivatives using the for diff package, which is basically like which basically define the derivative, and then you can take the derivative using the function. The other method of computing sensitivity is the go back. Okay. So the other method of taking sensitivity is using the interpolating adjoint method. So this is a reverse mode auto differentiation. So in neural networks, in this comes at the end of the course, there is something called backward. You compute the solution of the cost, and then you do backward propagation. This is basically a way of computing the derivative using an algorithm that computes backward from a given solution. So you move forward, you compute the solution, you find the solution of each point of each layer, you find the solution of each layer of your function, and when you go backward, because you know the solution for each layer, you can just compute the derivative for at that point, and then you can learn more about that in the MIT course and also later in the course today. So basically, like the idea is that like when there are many parameters, like more than 100, for automatic mode differentiation can be very expensive, because like you have to compute a very big Hessian, and the Hessian sometimes is like in a lot of times it's sparse, but in case it can be expensive. Now, when you're doing the backward propagation, you basically have to update your derivative every time. But once you compute the kind of the graph of the computation, then it's much more efficient to take the derivative. So because here I have 252 parameters, instead of using the forward sensitivity method, I'm using the backward sensitivity method. And then it's called interpolating adjoint, because adjoint is another way. It's another name for the backward propagation, and then I'm using the reverse differential vector Jacobian product. This was since VG before. In any case, this is a very, very superficial discussion of the topic. I recommend that if you're interested, you visit this link, and then you can maybe read a little bit more about like what's in it, how to choose the correct adjoint given the size of your parameter sets, and there's like the same way that there's different solvers, there's different adjoints. and then you just have to figure out which one is the best for your problem. But in most cases, the rule of thumb is like if it's less than 100 or so, you want to use the forward mode, and then if it's more than 100, you want to use the reverse differential, the reverse the backward. So and this so here it says like so this page is quite informative about the differences. So is that more or less clear, like what the sensitivity algorithm is for? All right, then assume that it's okay with everybody. All right, then once I define my so once I define my loss, then I can basically train my model. And then that one will take takes a little bit of time because I'm only running my local machine. I think if you run more powerful computer, is faster. So I mean, it's not instantaneous, but it's also not that slow. So while we're waiting for it, I already pre-computed it. So you can see like the loss actually goes down very fast. So by the time we reach, so the first 300, we are doing gradient descent with Adam, and then the last 300 we're doing with BFGS. So Adam will find more or less a point around the local optimal, and then BFGS will kind of like fine tune it. And then that's the way the SciML training does it. Like the researchers, the developers found that this more optimal way of doing gradient descent for the solvers. Then also the sensitivities. So I mean the derivatives, you mean? Okay. So if you go to, I never actually needed to use it, but if you go to the package, the differential equations here, and then you look at the solution interface here, solution handling, and then it tells you how to compute the derivatives here. So when you say, well, I show you how to compute the solution. So solution T. So let's say you want to compute the solution, the derivative, then you want to use then you can call it like this. So in this case, the first, this is the solution, is the derivative 0. So if you want to know this first derivative, it would be would place 1 here. And then you can decide if you want to go left or right. And then I think like that, I'm not sure if you can pass the sensitivity algorithm in this case, but here it's but if you just want to know the derivative at a certain point, that's I guess how you would do it. I didn't go very deep into the documentation to know which algorithm they are using. But we can maybe discuss offline if you're like interested in that. But maybe this is a good point of entry for you. That helps? Does it help? So like maybe if if I look here at let's take a solution here. So I have a solution. So if I say like I want the derivative at point 10, then it gives the derivative. maybe yeah, maybe I need to dig a little bit more, but I get, but there's more, but it's probably the idea, like, and then I can help you navigate through the documentation if you, after you have more problems. Maybe let's try to pass it. Sometimes it's like it's a little bit of a try and error. Let's see if it works. No, it doesn't work. So I don't think it's that way, but yeah, that's the idea. That's how you do like. Why you need so here so when you compute so the document so the training algorithm will use that the sensitivity algorithm for computing the gradient. I'm not sure like behind the scenes like exactly how it's done, but again, if you look at the documentation, might help. So if you go again to the differential equations and then the solve function, then if you look at the so the sense algorithm is really just is the way you're gonna compute the sensitivity. So here so if you so this part, the mathematics of sensitivity analysis, that's where we did the documentation discuss like the sensitivity, how the sensitivity algorithm works, and the different types of sensitivity algorithms. Yeah, sense alg just indicates how you compute the derivatives. Yeah, so how you're gonna perform the sensitivity. Yeah, and I agree with you. I think it's a bit confusing. Like, why do you define the solve of the prediction and maybe not in the training function? I don't know. To be honest, I probably wanna we probably wanna maybe research a little bit more. I probably need to read the documentation, but maybe when you read the section also the local sensitivity analysis, there's a discussion here. Like maybe that would be helpful. Yeah, sometimes like there's a lot of like parameters and things that and it can be a bit overwhelming. But the good thing is that the documentation is quite extensive. So maybe if you read this part of the documentation, you get a better idea of like of why we have to pass it to right in the solve and not somewhere else. Yeah, and I'm probably want to read that at some point because yeah, there's so many things to learn and I haven't actually mastered everything. Okay, so here you can see that the loss goes down very quickly, and then like around 300, like we switch from Aden to beef jazz, so that's why we get we get this like little dip here, but in any case. All right, so like we can actually plot the results. And then as you can see, because it's a new fitted solution, it takes a while to plot, but after the first time it goes faster. So what we find is basically like that our model fits very well to the data that we have observed, but when we extrapolate when we extrapolate the model, it underfits the rest of the solution. So the idea is that like we have computed from 0 to 10, and it fits reasonably well. But then after time step 10, from 10 to 50, the fit is just terrible. like we get the cycles and everything, but again, because we're using like a neural network as a function. Okay. You mean that it's just interpolation here in this graph? I didn't quite get the last. I didn't get your last comments there. So this is not interpolation. So after I find the parameters, I solve the system using the complete time span. So actually, like, I use the time span that goes from 0 to 100 to 50, 0 to 50. So I solve the problem, the neural network problem, with the initial conditions, the parameters that I fitted, and the original time span. Yeah, why the solution is so bad is exactly the idea that we are actually overfitting the solution. So like the neural network will approximate the function when we're observing the neural network will approximate the function very precisely for the data points that we have. But beyond that, like, nothing guarantees that our solution will match our model. Because, like, to begin with, we didn't know what the model looked like. So the neural network just tried to approximate just that part that it can observe. So here maybe here use a function that does that, but then beyond this period of time, it just does something else. So this example kind of illustrates like exactly like the problems of only using neural networks, because you might think you fit your data very well, but then if you extrapolate your solution, like, then the fit is really bad, and it has nothing to do with interpolation, but it's more like the function that we find with the neural network is actually like because a function can be anything, like, so if you think about function, a function could look something like this between certain period, and could look like something else in a different period. Like, a function only needs to be continuous and needs to map to you have that's possible. Maybe your plot is a bit better. It can happen um, uh, because the algorithm, the gradient descent, is sensitive to the initial conditions. So like, I actually run it different multiple times, and I end up with different plots. But in most of the cases, I mean, if you want to share your plots, um, like, in most of the cases, like, the main idea is that, like, it will fit the first section of the plot very well, and then after that, it varies a lot. Like, sometimes I will run the same algorithm and it will actually fit better. Some other times I will run it and it will be just flat. It doesn't really have a pattern, because the way the gradient descent works, it doesn't really find the best. We never know what's going to be the global minima. It only finds like a local minima. Although, like, although the algorithm is more likely to find a global minimum than other types, it's still like not 100%. Like, so you're never gonna get the exact same solution, especially outside of the observed period. All right, then maybe we give another break, and then we'll continue the last part, maybe the last part of the course in 5 minutes. So if you come back at 3:10, 3:11 actually. Is that fine? If you have any questions, please write here in the chat, and then we can discuss about it after the break. Thanks. Okay, so back. So, so one of you shared your the results. So actually, like, so I think this is like kind of possible. This type of result, like you can see that the function sort of fits well in the beginning, but then the fit really like gets worse after period 10. And it's also possible that, like, depending on the initial conditions, that that you might actually that you might not fit the observed period so well. So when you train this type of functions, it's a good idea to try different initial conditions until you get a training with very low cost. Like, because my experience is that, like, it's very sensitive to the initial conditions, and then if you initialize your network with certain parameters, you might end up with stuck in a certain local minima, and you're not going to be able to descend, and then I will just restart the parameters and I'll try to run again. And then I know when the cost reaches close to zero, then I know that it has kind of like converged, but sometimes it can be a bit tricky, and that's why it's this field is still like there's still a lot of development in this research area, because it's not very easy sometimes to fit the ordinary equation, the equations, and especially when you don't know what they're supposed to look like. So your only guide is the cost, and then if you see, like, sometimes your cost will be stuck at a very high level, and that's a bad sign, and you want to restart and run again until your costs gets very low. And we're gonna see some problems with training in the next section now. So if there's anybody has maybe other questions or comments or issues. All right, then let's continue. So with the universal differential, so let's assume that you have some knowledge of the system. So in the previous section, I said that, like, maybe we don't know anything about the system, but in some cases you have a fairly good idea about some things, but not such good ideas about other things. In this case, you might have a good idea about how the rabbits population is born, and then how fast the fox population dies, and you kind of know, like, that the rabbits don't depend on anything to grow, and then the fox also have no predator. So really what you're interested is to model the interaction between rabbits and fox, whereas you know well about the other condition, other parts of the system. So there's a paper that was published last year that proposed what's called the Universal Differential equation, and it basically is a general method for combining parts of the system that you know with parts that you don't know, and obtaining, like, a good fit. So we'll explore an example now with the logical Terra. So here we define a slightly smaller network. So we're gonna use an RBF function, it's a radio basis function, and then we're gonna define, like, a small chain. So it has to start with two, and then it has, like, two hidden layers, and then it finishes with a linear layer. So here we go back to the original formulation of the law of motion with the du option. And then in this case, we will compute this equation in the following way. So first we take the parameters of the function, and here we define the parameters only in terms of the neural network parameters, and then we hard code the true parameters. So we compute the output of the neural network, and then we add that to the function. So alt1 plus the true specification, and then here you have the death rate plus the network diagonal of this one. Yeah, maybe here I didn't use the right notation, but what I meant is so here you have a 2 by 1 times 1 by 2. So you end up with a 2 by 2 vector. Yeah, I think it should be the diagram. Yeah, I guess what I meant here is like the pointwise multiplication. Yeah. So sorry about that. Yeah. Okay. So all right, then we have the OD problem. Again, we define that the OD, and then here we're gonna start. We're gonna define. We're gonna initialize the loss vector of losses, and then we're gonna initialize a new callback function. So with the true solution, with our UD problem, and then our observation steps, and finally we're gonna initialize the parameters. So in this case, you can see like that that our initial parameter is really like. So the initial parameter is like if you look at the initial parameters, so UD in its P, they are relatively small. So our network will be more or less 0. So no matter what time, because the parameters haven't been trained. But then what happens is that like we have this parts of the network. So like we have the alpha and the delta, and can add a 0 here. So we have the alpha and the delta here. It means that like if this is very close to 0, the neural network, then it means that like the rabbit population is gonna grow exponentially large with alpha, and then it's gonna grow exponentially, and then the flux will decrease exponentially fast. So at the end of the day, our initial conditions imply that that our rabbit and fox population will so the rabbit will kind of like so the fox population will kind of like stay around 0, so die very fast, and then the rabbits will like decrease exponentially fast, probably driven by the neural network here. But the main point is that like this is very difficult to train, because everything here in the beginning is very close to 0, and then right at the end of the observation period, you have like such a massive gap, and this gap is only composed of maybe 4 points. So when you're doing gradient descent and you're trying to fit this part of the equation, it won't be able to do it very easily because the cost function will be dominated by only these 3 or 4 points. So you must take a different approach to gradient descent. So one approach proposed in the documentation is to do the following. So here we're going to use a sensitivity algorithm. We're going to use the forward diff because we only have much less parameters than before. So if you look at the number of parameters we only have 87, and before we had 252, and then we're gonna compute the loss the same way. but what we're doing different now is that like we have now a closure here. So we're gonna start with the last. Last is like the last observation period. So we're gonna train our model in steps. So first we're gonna model the 10 first initial data points. Then we're gonna model the 20 first initial data points, and then only at the end we're gonna model everything, like all the 30 data points. So this is what it. So that's why we created disclosure. So we're gonna pass like last will be like 10, and then 20, and finally 30. And then you basically compute will output the prediction function and the loss function. And then we're gonna proceed the following way. So we first train the 10 first observations, and then you say the UD loss for the first 10. And then we start with our initial parameters. And then we do 250 times, we do 250 iterations. Once we complete training, we're gonna pass the parameters to as an array, and then we're gonna train it again using now 20 observations. And once we do that, we're gonna go back and train with the whole data set. So this is a good way of like it's a good trick to do, like to avoid this problem that I just described. And then there's more tricks and tips on this part of the documentation. And in my experience, I think that's always quite hard to train the network. So except for the trivial case like the one before, when you're incorporating knowledge and you have different things moving around, I don't know, I find it very tricky. So you start with different. So here when I run this, I'm not going to run it again, because when I run this, sometimes with a certain set of initial parameters it works, and then the function converts. Some other times I will run and then you'll be stuck in a local minima. So that's so when you run for the first 10 observations, you're gonna see the error decreasing very fast. So as is the case here. And then when you train for the 20 observations, the error tends to start large, and then sometimes it decreases like here, and then you know it's going well. Sometimes the error will stay around that 60 or 100, and it will not decrease, and then you know that something is not going well. But if you manage to, if the error, the cost function reduces well in the beginning, so you reach like around 2 or 5, so less than 10. Then when you train with other observations, you're gonna start from a good starting point, and then usually like you start with somehow higher error, but then it kind of like converges fairly quick. So your mileage may vary, and you might have to restart the parameters many times until you get a set of parameters that have good convergence properties. So my basics for me it's still a little bit of a black magic, black art to get the function to converge, but I think like as there are more developments coming out, it will become easier. Yeah. So once we do that, like as you can see, the function fits pretty well for observed period. But when and then when you look at the full observation period, you see like the function will fit a bit better than before. So here again, like I could also run this many times until I get like very low cost. But here you see like the cost is already very low, and still my function didn't really converge. So I could run it multiple times it might never find the correct solution. Whereas here, because I'm incorporating some prior assumptions about the law of motions, my function actually fits a little bit better when I manage to reduce the cost significantly. So that's one of the first things to observe uh, when you training a model that's only based on a neural network and a model that incorporates some partial knowledge. Okay, so so that completes the part of the universal differential equations on how to train them. So the second part would be to make it more sparse. Ideally, we don't want to have neural net. We don't want to express our model in terms of a neural network because it's not very robust. Like small changes to the weights of the neural network can produce very significant changes to the result. So it's that thing that we discussed at the beginning of the course that the sensitivity to initial conditions. So here we're dealing with a neural network that has many parameters. So you mean you could plot the face portrait if you wanted, but I have not done that before. But I think it's not so, it's probably not a good way to. Yeah, yeah, I don't know. I think like I think like what you're fitting really is the sum of square errors. So there is no, so in that sense, like I'm not sure if like you could plot the observation systems of the face portrait, but at the end of the day, your loss function is basically your observations minus your prediction. So like there's nothing really, there's nothing about like the portraits versus the trajectory. But if you can define your loss function in a different way, that maybe makes more sense. So the prediction could be so yeah. Well, I still don't get the question, but like what I can say is that like that your prediction is basically you have to output something that you can compare with the data. So your loss function has to basically you want to compare the error between your prediction and your observation. So like because your observation comes in terms of a trajectory, when you want to compute your prediction in terms of trajectory. I guess if your observation came in a different form, such as a face portrait, then maybe you could then use a face portrait to compute the error. So yeah, maybe it's not a very satisfactory answer, but otherwise. Yeah, yeah. I mean, like, yeah. I mean, you mean the portrait is this one, no? Like, the phase is this one. So, but this is like this is basically like a trajectory. It's just like instead of computing the XYZ plan, you're computing the because like I could do like a 3D plot as well. Like so actually like the trajectory looks like that. So okay, so what do you mean is like, oh, what if like I know that the solution is cyclical, so why don't I just then fit to the cyclical parts? Okay, so if you know the solution is cyclical, you know something about the model. So you know more than not knowing anything. So I mean, you could go and say like, okay, like I fit the 10 first points, and I know that from now on the solution will be cyclical, so we'll follow the same trend. So I just like repeat the neural network every 10 observations. So you basically fit using a sine function to assign, basically using a combination of sine and the neural network to define your model. There's nothing wrong with that if you believe that the function behaves like that. but this is a very simple illustration. So in reality, you would not know how if your function is cyclical. So the problems that, yeah, in a sense, yeah, that's true. Like the problem is undetermined if you don't assume anything. But also like but actually if you have a observation points and you only want to really know like how the function behaves in that interval, then of course like the function is not undetermined. But like yeah, beyond that observation period, yeah, maybe you could argue that the problem is undetermined. Uh, but but we know in reality that that there's a law behind it. Like so if you believe in sciences, we know that there's some sort of like explanation for what we're observing. But and then we sort of have to make assumptions about what we expect about what we're observing. So in that case, in this case, in this model, we might know more, and we might assume that yes, the function must be cyclical. But maybe we don't know like if we are observing a full period, or if maybe we're observing only half of the period. So it depends what kind of assumptions you're making. But that the main takeaway is that like you want to incorporate some knowledge that you might have about the system, and you want to use the neural network to fill in with the rest of the details. So or to fill in the very non-linear parts of the model that you don't know. So yeah, if the problem is to determine like what is the reason to fit in. Yeah, I mean like a lot of the like yeah, this is a set of tools. So like you would need to know. So what are you looking for? So usually you have some assumptions about how the model behaves or what how the reality operates. So you're like you're modeling some sort of interactions, and the data you collect, you have some knowledge about about how representative it is of the whole space. But like yeah, if you're super skeptical and then you think that your data is biased to a certain part of the space, then I guess like you could argue that the model is indeterminate. But even then, like maybe then you're building a surrogate model for only for you're building a surrogate model that will fit the observations for that period, but it will not necessarily generalize. And, and to be honest, like that's the biggest challenge in science, is to know if your model is actually generalizable, if it makes sense, and it's just not like you're just not fitting your explanation to what you observe. And I guess a lot of the criticism to machine learning is exactly that, like that the models, they don't generalize, they only fit to the data they're given to. Mm, but yeah, so that's where I'm gonna cover in the last part of the course. So like I'm glad that we touched on this problem of undeterminacy, of the undetermination of the problem, because like one approach in science is to assume that like okay, I don't really know, I don't know a lot about the model, but I'm looking for a sparse explanation. I'm looking for for a robust set of like equations that could represent my model. Uh, so there's like come like the sparse identification of nonlinear dynamical systems. So in that case, like we start with we mix like so in this case, like we start from a different set of assumptions. So we could project our function, our fitted function, to a set of basis functions that are a sparse representation of the neural network. So for instance, like if I'm talking about the Taylor series, as we know, any polynomial function, as you might know, any polynomial function can be fit with a Taylor expansion, and in the Taylor expansion, we have like we have that we can represent as a polynomial of k degrees, and then like we could take that neural network and then approximate to the Taylor expansion, but only up to a certain degree. So that's a good way of like making the model simpler, and then only retaining the most important part of it. Another way of approximating a model is to use the Taylor the Fourier series. So we can express the model in terms of cosines and sines. So as you say, like, so let's say we can incorporate the assumption that okay, my model is cyclical, so it could be approximated somehow with the sine function, and then I would like to fit my neural network that's super complex with with the spaces which are much simpler. So here is another representation, so we can represent any function in terms of sines and cosines. So if we generalize this idea, like we could represent any function using a set of basis functions. This set of basis functions are usually orthogonal to one another, and then we have and then we have a coefficient matrix. So for each basis function, we could assign a coefficient that would allow us to model our observations. So we just like trying to find our law of motion using a restricted set of basis functions that could replicate a very large number of functions. In a sense, we're taking a very similar approach than our neural network, but in this case, we're trying to use a sparse set of like functions, whereas in the neural network, we kind of going the other way around. We like being very very generous about the type of function that we allow, and then we just try to approximate it as closely as possible. So the sparse identification can be constructed as an optimization problem in which we try to find the coefficients that will minimize this linear regression, and then we add regularizers to ensure that we only obtain a sparse number of regressors. So the L1 norm will ensure that most of the coefficients are 0. So this is a good approach. This is also an approach that has been explored in the literature of like fitting differential equations. So rather than use a neural network, we could use the dictionary method. So in practice, again, like there's problems like now that you run this function, we need to compute the finite difference for x, and then we might face some numerical errors when computing x. Also, the number of states n might be prohibitively large, so the number of parameters, and again the number of the base functions grows arbitrarily large, whereas for neural networks is constant. So here, if you think about Taylor series, you basically have like for every combination of for every number of dimensions, we basically have a combinatorial problem of in terms of the number of allowed polynomials. So you can have x1 times x squared, and then you can have x2 times x squared, x1 squared, x2 squared. And then if you have a cube, you can have a cube times the square becomes a linear function, so it grows exponentially large. Whereas with the neural networks, the number of parameters is fixed given the depth. Okay, so the way to do that, Julia, so here, so our approach here is like we're not going to try to approximate the whole function, but we're only going to try to approximate the interaction that we found in this part of the workshop. We're going to try to approximate it with a set of basis functions. So try to sparsify that the set of like our functions to see if we can be generalized better. So to do that, we're going to use a few libraries. So the modeling toolkit is for defining models. The data-driven defect is where you have your sparse identification of functions. So with the modeling toolkit, we can define variables. So here we define a variable x, which is so we define two variables x, 1, 2, and then we define a basis. So that would be this part here, the theta. So and then now you can print the basis. So like, so if you look at the basis, is something like this. So it's so it starts with 1, the next. So you see, like you have 23 different vectors. So it's basically like a combination of every single one of them. So the constant one. Then you have the x1, the x1 square, x1 cube, x1 to the power 4, then 5, and then for x2, and then we have a combination of x1 and x2, the combination of the polynomials. So as you can see, it can grow arbitrarily large. Okay. The nice thing is that with Julia, you can just call the polynomial basis, and we'll find out the possible combinations for you. Also, you notice that like x is a variable, so actually, if you print it, it will show you like x1, 2, and then it's just like a way of like defining your variables in the models. There's a talk, the Julia Conf this year. There's a talk about using modeling toolkit for other types of modeling, so I recommend it. Okay, so now what we're gonna do is we just want to look at the interactions. So the part that we don't know about. So if we are not only solve the UD problem. So here, so it's basically doing this part of the problem. So and so you have these observations. So how do you compute the interaction? So the true interactions are computed using the formula. So here you just compute it with the formula. So like we know what the observations for each period, and you know the parameters, so you just compute it. And then for the UDE, we know what the observation prediction is, and then you know the parameters that we found before, so we can predict the interaction. And then we can plot it. So you see the true interaction and the predicted interaction, they look basically the same. And then you can compute the error like between the true interaction and prediction. So these two plots would not be available in real life. So these are just for illustration purpose. And then finally we'll define our sparse unification. So we use so rather than using so I mentioned that we use seem to use L1 norm, but the L1 norm is not differentiable. So because you're using like the modules operator, which has a kink. So a way of optimizing this function, or maybe an alternative algorithm, is to use what's called a sequentially threshold least square. So you use the two norm and you use like a threshold, and then you start with a very permissive set of very permissive permissive how to say call, weight, the lambda, and then you decrease and then you increase it such that such that you allow less and less that you increase the cost of having a large number of parameters. So in this case, I end up with all this cost. So I start with a very small cost, and then I end up with a very large one. And then I start the optimization, initialized optimization object. We call it STLSQ, which is defined by the data-driven package. The data-driven package then also defines the continuous data-driven problem, and then we pass our observation, our predictions, and then our observation steps. So notice that here we're not passing any data, any. Okay, so now we want to make sure that the model works for the true that Cindy will recover the true parameters if we pass the true data. So if you remember here, we computed the interaction true. So we will have that we pass the prediction the predicted our observations here, the predicted observations, then the steps, and then the true interaction. So here the true interaction is computed using the predicted observations. So we look at the predicted observations. So that will give you the state of the model at a given point in time, and then we know how to compute the true interaction using the true parameters. So that's what I mean by that's why we're using the predicted observation. But then our dx is basically like the true interaction. So the true interaction of the predicted observation. So we can solve this. So you use a true Cindy problem, the basis that we defined before, and then our optimization algorithm. And then if you run, we can see that we actually are able to recover exactly the algorithm exactly, the data exactly. So now if we move on to now we're looking at the predicted interaction. So the predicted interaction is computed using the neural network that we defined in the previous sections. So it's this neural network here. So our predicted interaction will be passed as the dx. So dx, when you see dx there, meaning you should think about this one here. And when you think about the basis, you can think about this one, and the coefficients are these ones. So you pass the observations, the steps, and then the interaction, the predicted, and then we solve, and then we find the prediction. And you see like that our sparsified model will find the true parameters. And so then if of course, because I found the true parameters, if I plot it, then I'll get basically the same, very close to the, because like I modified the true solution above because I rerun it, but you can see like it's basically the same solution. All right, then yeah, I just want to show you that like it's not always the case that Cindy will find the true solution. Like here we were able to find the true solution because like as we saw, like the interaction, the predicted interaction they mesh very closely, and then like it is contained inside of our basis our hypothesized space. There's a very large number of bases, but it was able to like figure out which bases are relevant, and then it found the correct parameters. But in the case where we didn't know anything, so we started with a neural network, we can basically perform the same exercise. So we first computed two derivatives. First computed two derivatives using using our observation. So we started with an empty matrix, and then for each column of the matrix, we want to compute the derivative. So we will call the function LV, and then LV will modify the du. Remember, it modifies du, and du is a column of this matrix. And so it was signed du. I'll give you the observation at that time at that step I, and then it will use the true parameters to compute du. So I can define then the true Cindy problem. So you have the observations, the steps, and then you have the differential. And notice here that I'm not computing the interaction, but I'm actually computing the true differential. So because like I don't know, because in this model I don't know if there's an interaction or not. So I just know how the whole thing changes. So I'm here computing the whole differential. So if I pass the true data and the true differential, you can see that the model, we can recover the model exactly. And then but then now, like if you use a neural network, that the neural network they used to fit the full system, and we didn't know anything about it. And then we compute the errors. You can see the errors here. And then if we compute if we use Cindy then to try to find a solution, like we end up like kind of partially find some parts of the solution are correct. So like P1 and P2 are correct. But then we also find the law of motion for the foxes are not quite accurate. So like we find the 0.3, and then we find like a very more complicated interactions than the true model. And then like and then if we kind of plot the solution, like you see like that they don't match at all. So basically that completes like the whole like workshop in terms of like fitting a neural Ds, sparsifying neural Ds. And then like I would like to address also your question about like what it seems like the model is always in the problem is determined, like it's like what should we do about it? So there's a theorem in mathematics called the no free lunch theorem. So the theorem basically says that like there's no free lunch, meaning that that like either an algorithm will be very good to will fit the observed data very well, leaving no gaps, but then maybe you cannot generalize it to every problem. So it states that any two optimization algorithms are equivalent when the performance is average across all possible problems. So you can have an algorithm that fits the data that you have very well, but it's not gonna maybe generalize to others. Whereas you can have an algorithm that it doesn't perform so well for the data that you have, but then it's more generalizable. So there's a trade-off between like overfitting and generalization, between fitting and generalization, and where you draw the line, it's up to you as a researcher. When you're trying to find new laws from data, you want to bring your previous knowledge from the field to the data, and you want to then take advantage of the machine learning to fit the parts of the data that are unknown, that are more complicated, and then you want to balance this the fitting with the explanation. So is there any questions maybe for this for this part? Okay. So I don't know. Like maybe since we're not many people, I'm wondering like if you like the last section of the course is rather is more like mathematical intense. I don't know if it's worth going through it. Maybe because we spent a whole day here, it might be a bit tiring. So why don't you tell me if you want to cover that part or if we should call it a day. I mean, now it's 4 o'clock. We probably would need another hour or so. So, so and then of course you can read it and we can discuss it offline or something. If you think that if you think you like it might be too much today or something. So I'll let you tell me. Okay then. All right then. Let's take a break then. Let's do another 5 minutes. Then come back. Then we complete all the slides. Right then. Maybe come back at for maybe let's take a 10 minutes break. So 4:10, and then we just cover the last part. All right. So see you soon. Okay, I'm back. Hello. So, so cover the. So this is the last part of the workshop. So thank you if you made it so far for all the attention. It's really good to present all of that. So as Jonathan said, it's good for us PhDs to practice and to make sure that we have a clear understanding of the thing that we are researching and teaching actually helps. So the final part of the course will be a bit more technical, and we'll cover the mathematics behind neuro-ODs. So I'm saying that it's gonna be a bit technical, but like not be overly complete. I think it will not be overly technical, like if you're expecting a lot of like proofs and all that. It would be just more of a discussion of like some of the ideas behind. So when the first thing is like the solution to ordinary differential equation. So I claim that there is a unique solution given the law of motion. So I didn't really define the properties of F, but I've in order for us to have a unique solution of F must be uniformly continuous distribution around the initial condition, and it must be Lipschitz on X. So basically saying that that F must change smoothly. The nice thing is like so when I say X here, I mean U. So what we're saying is that like when F whenever we so Lipschitz means that like when we move from state U1 to state U2, like the is bounded by a certain constant K. So our function does not grow arbitrarily large, but actually like so if you divide the fu1 minus fu2 by u1 and u2, and then we drive it, and then you drive u1 u2 to an arbitrarily small interval, then basically defining the derivative, and basically we're saying that the function has a bounded derivative. But Lipschitz actually implies it is a bit more permissive in terms of the fact that there are functions that are Lipschitz continuous but not differentiable. So we're saying that like it's differentiable almost everywhere. So there are some points where the derivative might not be defined, and that's why we cannot define we cannot define this expression in terms of a derivative, but it has to be, it's in terms of a bound. So that's good because our OD basically then covers almost every function that is differentiable, and when talking about continuous changes, I think like that we are interested in continuous and functions that are continuous and basically differentiable almost everywhere. And I think that's also part of the reason why we don't model economics time series in terms of ODs, because there's a lot, in a lot of the cases the function changes up very fast, and although it's yeah, it changes very fast, and then maybe it's not Lipschitz continuous. So okay, so so the second part of the discussion is with regards to the gradient descent. So what I'm actually trying to achieve when I say that that we did gradient descent on the solver. So we can think about the cost function as a function that goes from the parameters our parameters and our state. So it goes from n and k to a single value, so r. So we're mapping like the set of parameters that we have, they're assuming, and the observations to the solution to a number. So that's the cost function. And then we also in our problem, our solution must satisfy its arbitrary conditions. So so in this case, f u p equals 0, like if you're talking about OD, basically saying that the du dt minus fu equals 0. So are we going to see an application of that to ODs just a few slides down? So that's good. So like we have this very general cost function, and then we have also established an arbitrary condition that our solution u must satisfy. So we could define this problem. So now we're trying to find the parameters, because that's the only thing we can modify that will drive our cost very close to 0, subject to satisfying the conditions. So u is actually a function of p. So that's why we don't try to minimize u. Yeah. So the problem then can be formulated as a Lagrangian. So we define as the cost g minus lambda times f. Because f equals to 0, we're basically saying that we're trying to minimize the cost function minus some arbitrary some function that is always equal to 0. But that's good, because when we define our problem in terms of the Lagrangian, we now have a problem that we can differentiate, and we have a single function, and that's much easier to solve than the first problem, where we had to maybe find a minimum for g and then check if it satisfies the constraint. So if you think about, now we're gonna think a little bit about backpropagation. So in practical terms, the way we solve this is through a gradient descent. So gradient descent is basically finding direction that we can modify p such that the cost decrease as fast as possible. So this is what the GDP is doing. So in order to do that, in order to find a direction that we want to descend, that we want to move, and because we want to be able to compute this value as quick as possible, and because g will change according to our parameters, like we must be able to define method that will do that for every iteration of our gradient descent. So, okay. Okay, so here I repeat like what I've described actually before in the slides. What are we doing when we're solving the ODE? So we first, like, given parameters, we solve a nonlinear system, and then we find x. So x is a function of p. So you notice that here x and p are must satisfy the constraints, so we can express x in terms of p. So in most cases, we use the Newton method to find the solution. Newton method is a method for finding the roots of the function, and here we're doing nothing more than finding the roots of the function. So you're probably gonna have to compute the derivative of this function. So we'll save it for later. Then we're gonna compute the cost once we know the solution in terms of p. And then we'll change the parameters in the direction of the steepest descent. So this will probably you probably need to compute the derivative for the constraint, and then the derivative for the cost function, and then in both in terms of the parameters and x, and then you keep doing that until you converge. So it's very simple. So this algorithm is what we've been doing. This is what we've been doing all the time, just stated in a general form. So in order to advance, we could define a few useful definitions. So if we want, so the first definition is the x bar. So it represents the derivative of an intermediate variable with relation to the cost function. So our cost function, the cost function is the ultimate goal of our program. So we want to minimize it. So every derivative we want to compute will be with regards to the cost function. So we denote this derivative as x bar. The second thing is like we're gonna define is what we call the pullback of x at the point x. So it's defined as b x f y. So maybe we can break. And I'm using this definition from the original paper from critical calculus, the universal differential equation. So if you look at this definition, we're saying that this is a function of y, but it's a function of y that depends on certain parameters. So f and x. F is the function for which to find the pullback, and x is the value of is a value that is a value for is the value that we're interested in. So like if you computed the function fx at a certain value, then we might want to modify. Then we might want to keep x fixed, and then just change y and see like which direction we are moving. So we're basically saying like we compute we basically compute the derivative of x of f at point x. So this is then become a parameter. It will become like a fixed a fixed value, and then we multiply that by our input y. So that's a way of saying. That's another way of saying like we compute the derivative of y with regards to x, because y equals fx, and then we multiply that by y. So that's the pullback. And why we wanna define this this strange looking function, which is a derivative times a vector? Well, basically this comes from the chain rule. So the chain rule says is that the chain rule says we start with the cost function. So here probably should be big G. So the big G is equal to, so the derivative of the cost with regards to y is equal to y is equal to the derivative of y with respect to x. So sorry. So the chain function says that so we wanna find the derivative of the cost function with regards to x. So that will be delta g delta x. So according to the chain function, if we know that g as a function of y, which is then a function of and then y is a function of x, as stated here, and we can decompose using the chain function. So delta g delta y times delta y delta x, and then basically this is this will be equal to x bar. So like we just use the definition here. So y bar as we define here is delta g over delta g delta y. So that will be y bar, and then delta y delta x is it comes from the definition of the pullback. So if we cancel the delta y, what we have is delta g delta x, and that's the pullback. why is just like a generic it's just like an intermediate value. Like you might compute the so when we have a neural network, like we have many hidden layers. So like X could be the initial inputs, then Fx will be an intermediate input, and then we express Fx using the variable Y, and so on and so forth. So the idea is that like because we're going back down, we're going down a chain. We basically like defining like for each step of the chain, like what is the change to the cost function. Yeah. So okay, so this is so this definition is just a way of like defining the backward propagation algorithm in terms of like a mathematical, using mathematical terms. So we just like computing the, we're trying to compute the derivative of the cost function with regards to any of its inputs, starting from the walking backwards. So using the chain rule backwards. So okay, so given your conditions, okay, so given your conditions, we can so as I mentioned before, like the u is implicitly defined by p because of the constraint, everything needs to be equal to 0. So if we take the derivative with respect to p, it must be true that if this must always be 0. If we change u, if we modify p, then in one direction, then we have to decrease p. So if we modify p, and then u must change in the same at the same rate that f changes. So that at the end of the day we end up with 0. And then like now we can, giving all these definitions, we can then compute the direction of stiff descent for the cost function. So ultimately our parameters are p. Everything in we can think that everything in our system depends on the parameters. If it did, and then we can then now derive our cost function. So the first thing is like, so using the chain rule, are the constraint at f equals 0. So the first part here, by the way, can you see my mouse? I keep, okay. So okay, so the first part of the chain rule is basically saying like what's the direct impact of the parameters in the cost function. So in most cases, the impact will be 0 because as we saw before, like the loss function is just sum of square between the errors and the observation. So in most cases, we probably want to ignore. It's probably going to be 0. But in any case, we can express this as p bar. And then the second part is what we're interested is what we say. How our cost function changes with our functions, which are, and then how our function u changes with the parameters. So the first part is u bar, so what we defined before, and then the second part comes from our constraint. So the udp will come from these constraints as defined here. So now we have an expression for how the costs change with regards to the parameter. So it's basically, I'm basically saying like the cost change. There's a change that's attributed directly to the parameters, and there's a change that comes through the function u. So, but that stands like this is a very expensive computation because if you're computing one item at a time, so fp, so that would be the hashing of the function in terms of the parameters. So sorry, that would be the derivative of the parameters f in regards to the parameters. So that's part of the sensitivity. You'll be computing a matrix of n n dimensions times p. Then the second one is the Hessian. So we end up with the second derivative of the law of so the first derivative of f, so is the second derivative of the law of motion. Or the second derivative of u. So that's a very big matrix. So it's m by m. And then finally, after we completed all that, we're just gonna reduce everything to a dimension of one. So by multiplying that with the by how you change with g, how you induce the change in g. So ideally, like we want to avoid these expensive computations or computing this big matrix and also multiplying these two, multiplying out this matrix together. So can we do better? And that's where backward propagation. That's where we get a that's where our sensitivity algorithm comes in. So if we if we define like this section here, we denote it as lambda, and then we can actually write can actually think of like lambda t, then we multiply both sides by fu. Then we can actually think of like lambda t fu as the pullback of f at u for lambda. So it is a vector Jacobian product. Also another name. So when you look at the code, you have the VGP, etc. True. So when I'm looking at the sensitivity algorithm, I set this function here. So I said reverse diff vector Jacobian product equals to true. So that's what VGP stands for. Like is this vector Jacobian. So I'm basically computing the vector lambda times the Jacobian field, which is second derivative, or the Hessian. So now, okay, so now if you know fu and u bar, the vector lambda can be efficiently computed as a solution. So we basically like we basically can just solve this linear system to find lambda very efficiently, rather than computing the whole Hessian and then computing the derivative of chi. And that's what makes it the computation more efficient. Even though we are kind of doing, even though it feels like we're just manipulating numbers, we're just like actually trying to write the whole thing in a way that is that's more efficient, in which we make less computation. And so okay, so our the sensitivity of g to the parameters p, so the direction of the direction in which the cost changes the current p can then basically be written as the direct impact of the parameters of the cost minus the pullback that is induced by lambda. So you might ask yourself, okay, but what's lambda? Like you just came up with this variable out of the blue. I mean, clearly it's is a vector times a hash, but in terms of, right, is there a intuitive interpretation? And the answer is yes. So if you think that the constraint, if you think that the function f u p could be anything, like, so now you're not thinking about the constraint, but you're just saying like, so the value of fup is equal to v. So we're basically saying that the pullback of f, so the pullback of f on v, so how v could affect the cost function, will be equal then to u bar. So how do I know that? So I'm just saying, so I'm just comparing this expression that just comes from the definition. So this definition here. So that depends on the chain rule. Because like you see the pullback of f at x is basically it's a definition, and then I'm saying like, okay, at the value y, and y now it's just the y bar. So this is basically the same thing as saying like that's the impact of x on g through y. Sounds a bit complicated, but that's the idea. It's like the pullback of this pullback operator just means like is the impact of the variable x through y. Yes. And so I'm saying now here that the impact of v through u is that. So if you compare this expression, the expression above here, we can see that lambda then is equal to v. So in other words, I'm saying that lambda represents like this vector Jacobian product is this expression of the vector Jacobian product, but this expression here is the shadow cost of changing our constraint in a certain direction. So that agrees with the Lagrangian formulation, because here I derived everything without referencing the Lagrangian. But now that we understand that lambda is actually close to this shadow cost, and this is another way of saying this is another way of like deriving the Lagrangian. Okay, so after a lot of this discussion, like you might be wondering, like, okay, like, can you give me some sort of implementation, like what are you talking about? So when we talk about adjoint, that comes out a lot in this literature. What I mean by adjoint is basically the pullback. So what's the pullback of x? So again, pullback is the impact of whatever is the input through x. So it's the impact of x through whatever is your input. So what's the impact of x through lambda to your cost function? So the x bar. So if you have a constraint that specifies that ax minus b, so the adjoint of x then would be given by lambda transpose of a, because the derivative of this will be a, and then if you look at the definition of the pullback, is basically the transpose vector times the derivative. And so in this case, the expression, so we have this expression here that we were using before. So here I'm just comparing. So in Julia, the way to define pullbacks is you can use the library Zagatti, and then so use a library Zagatti, and then so I start with a random matrix A and then the vector X. So the pullback it will so you define the function of X, and then you define the value of X, because the pullback always is always defined for a fixed value of X, and then what the pullback will give you is the result, which is the derivative. No, is the result of applying the function, and then the derivative, and then the pullback function. So the back is a function like as I wrote here, generic function. So in the forward, when we did the forward pass, we fix x at 1. So the pullback is like given that x is 1, what's the impact on the cost through lambda. And then like we can so if you take lambda as a random vector, we can compute then the impact in the final cost like that. So the pullback will give you back a function. Right. And then here I show you that this is exactly like the definition of the pullback is you get the same thing. Okay. So when we okay, so I kind of like discussed the pullback operator and the cost optimization in generic terms. So now we can apply these ideas to the OD to ODs. So how do we do that? So we just map the generic formulation to this to the OD case. So the cost function in this case, it doesn't depend on the parameters; it only depends on the function u. And then we say that the cost function is basically a sum of a function that goes from our observer period, so 0 to t, and then for each time step is a function of like our it's a function of our solution. Could also include our observations here, because we just saying what's the function depends on, but like we're not saying other parameters of g. So to find a derivative, we can specify the Lagrangian like before. So in this case, the Lagrangian is defined in terms of the. So we have g, and then our constraints that the law of motion satisfies this expression. So u minus f must be equal to 0. So here we go, and then this must be true for every single point. So that's why we have the sum, and then the lambda is the Lagrangian weight. So if we compute the derivative, then we can just basically compute the derivative, and then we can reduce it through a lot of some algebra manipulation. We can reduce this expression to this expression. So basically saying what we described before. The way that our cost function changes with regards to the parameters is a direct effect of the parameters on the cost function. So it's this section here, and then we isolated the impact of the cost through the impact of the parameters through our function u. So this part here. So in order to solve this problem, we impose 2 additional conditions. They don't impact the optimization, since lambda, as we said before, multiplies an expression that's equal to 0. So lambda can in effect be anything. So we'll say that lambda t. So our shadow cost must be at the last time of the last observation period must be equal to 0. And then we're also going to say that this expression here must be equal to 0. So why do we want to do that? Because if you think about if this is equal to 0, if lambda follows this expression, then this is equal to 0, and this is also equal to 0, because lambda t is equal to 0, and then at time 0, our function, our derivative is also equal to 0, the du dp, because of the initial condition. So the initial condition, the parameters don't affect, don't change. Okay, so that means that like in effect everything here cancels if we impose these conditions, and you only end up with this true this expression here. And so our cost function at the end of the day is can be expressed as the pullback from the the direct cost of the direct impact of the parameters on the cost function, and then second the impact of the parameters, the impact of the parameters indirectly through lambda, so our shadow cost. So this gives us a recipe for finding the optimal parameters of the OD. So what we do is like we first find the solution of the OD using the solver like we had before. So we start with U0 equals 0, and then we obtain the solution UT. And then once we have UT, we can solve the OD for lambda. So we start backwards. So we know that then lambda T must be equal to 0. So we solve it backwards, and because we know U, we can compute the hash sum here. We can compute the direct impact of the of U on the cost function. And then finally, we can backpropagate lambda and integrate it to find the total cost. So this is what I mean by backpropagate. It's we put lambda here, so you compute the pullback, and then we integrate. So like we compute for the whole time period from 0 to t, like the total cost. Yeah, so the in a nutshell, that's how it works. I think like you probably want to read this a couple of times to fully understand it, and to be honest, like every time I come back, I have to like read it again and think over and over again, because it can be a bit confusing. So G so we didn't really specify what G could look like. In most cases, when we have discrete observations, we could what we have is that the expression G, like so the little G here. So here the little G is basically like a sum of like X observation minus U, our solution, only for the periods that we have an observation. And because of the direct delta function basically says that when Tn equals T, this is 1, otherwise it's 0. And so this can be reduced to basically a sum square, as we had originally. So in discrete cases, then our evaluation of lambda proceeds as following. So I said like you have to solve this equation, this OD here. So and then again, like you can write it as a pullback. So okay, so when we observe X, we have an extra impact of U through G, direct impact of the cost function of U parameter. Whereas when we don't have any observations, the only impact comes from the indirect impact through the constraint of U. Yeah, so these are when we doing this, there's because when we have this discrete formulation, you have to take this into account when you're doing when you find the solution. It is discussed in more details in the MIT course that I mentioned before. So this course and this one. Okay. Okay, so that completes the derivation when we have discrete observations. So what about the derivation in the original paper? So the neural Ds were introduced by Chen et al. In 2018, and in the paper they define a variable or a function a that is basically what we define in this slides as u bar. So it's a negative of u bar. And then they have that G is equal to F. So basically they don't have like a cost function. They just have the cost function is the constraint. Because what I have in mind there is image classification. So it's not solving all these that I presented here, but it is going back to the idea that you're replacing ResNet with all the differential equation. So what they need to do is so they use the differential equation as the main cost function. So then they derive the following expression. So they claim that to find in order to find the optimal parameters, you just have to solve this system of differential equations. So in fact, the system that we found before was defined in terms of lambda. So if you take the derivative of dg dp in terms of time, so remember this is p bar dg dp. That's the direct impact of the parameters of the cost. So there will be p bar, and then we can express this as that. So if you go back to the so this is the expression that they end up with, and then if we rewrite this, you see that we end up with an expression that looks very close to the expression here. Except that like they have the u bar, and then we have I plus lambda. So we previously find also the evolution of lambda, which is this one. Again, if you look at the expression here, it looks very similar. So like in our derivation, like lambda represents the shadow cost of modifier constraint. So it kind of covers so it kind of like puts the u and the t change together into a single constraint. And then we basically have a system that is equivalent to Chen et al. So it's just a different way of expressing the same thing. All right. So the final point I want to make is like, so how do you compute the reverse ordinary differential equation? So I said like, okay, you have to solve this system here, lambda t using, but how do you actually solve it? Like, it might be a bit. I didn't really discuss it, especially because like it seems like you need to compute the hash, because you have fu. But then again, like we came back to the case here. So like remember that we don't need to compute. We can sometimes just solve this expression, and then so this is just a system of linear equations. So let's go. So the first method is called the interpolating adjoint method. So it's called interpolating because the idea is that you interpolate to find the value of ut at certain given points in time. So you first find a solution for ut, and then you select, then you interpolate, then you select some time periods, and then you interpolate the solution between the time periods that you didn't compute the solution for. then to compute this expression here, the derivative of lambda, you need to compute the Jacobian of f, as I mentioned, and of g. So one option is you solve forward, so you basically computed the hashing. Alternatively, you want to compute the pullback. So for lambda t fu, what you're computing is the pullback of lambda through u. So that's so you do that via backpropagation, and then that's why it's called then the interpolating adjoint, because you use the interpolator to find the value of ut at the points of time that you need, and then you use the adjoint, so the pullback, to compute the derivative of so that you compute the fu at the points that you need. So you're not computing fu, you're just computing the whole thing, like lambda t fu. So that saves a lot of computation, because like you just computing so you basically computing the change in function, the function f through, yeah. So the second method is the backsolve method. So you can do you can solve u in reverse. So you red solve u forward. Now we put these two systems together, so the u and the lambda, and now you're gonna solve it backwards. So you're gonna solve for u again together with lambda. So we know the termination condition for ut because we solved it forward, and then we know the termination condition for lambda t because we have imposed that, and then we can solve. We can then compute the solution for u and t together, and I compute g. So the problem is that like the solution for u in forward and reverse mode, they do not always agree because of the stability of the solver. So the back solve method is sometimes not very robust. Yeah, so this is basically this was a discussion of like what's happening behind the scenes for when we're optimizing when you try to find the optimal parameters of the system using I guess not only the neural networks, but any function we're trying to optimize for. And neural networks is one of them, and because of the large number of parameters, we always interested in finding efficient methods. And then I encourage you, maybe if you want to learn more about it, to go through the documentation. I guess reread the slides. For me, also like, yeah, it's always a process of like going through the math and trying again over and over again to kind of like a little bit of that sinks in. So in conclusion, at this point of the workshop, so at the end of the workshop, I hope that you have developed a basic understanding of ordinary differential equations. You can identify and frame problems of a differential equation. So maybe think about if you can tell the difference between solving an ODE and feeding the data to the ODE. So sometimes you're not very familiar, you might mix things, both things, and at least with me, when I was learning it, I tended to mix those two things together. So the second is you're able to use Trigger for scientific machine learning. Hopefully you can tell what are some of the most popular libraries, and you can formulate to solve a basic OD problem and hopefully you can you know where to find more documentation and more help to continue your journey. And you can understand the role of neural networks in fitting ODs. So you know, like, where it might be good to use neural networks, how you can incorporate some knowledge of the system in there, and what's the role of sparse identification for simplifying the solutions you find through using neural networks. So what's next? So even though we covered a lot today, actually we only scratched the surface, and there's a lot to be learned. So for a start, you can ODs are there are ODs in multiple dimensions, and actually, like, a lot of the systems, they are not periodic, but they are chaotic, and chaos means that so like in the case of the Lorentz attractor, there's no cyclical pattern. So like once the system reaches the attractor, it goes it moves in a certain pattern that is not periodic. And then if you start in slightly different conditions, you might end up in different positions of the system after a certain point in time. So the second one is bifurcation theory. Is the study of how parameters can change, how small modifications to a parameter can change its solution. So it's related with finding the optimal parameters, but now instead of like trying to fit the data to the system, you're more like trying to study how the parameters change the system, and what are the points that the parameter can produce qualitative change. Then apart from all these, we have partial differential equations. These are differential equations which there are multiple independent variables, and the canonical example is the heat equation. So it describes how heat dissipates in a material, and then a basic understanding of ODs is a requirement for understanding PD, partial differential equations. So if you want to learn more about universal differential equations, I welcome you to go to the GitHub repository of the authors of the UD paper. There's plenty of examples here, even more even more complex examples from different fields. So so climate field and all that. So here it's an example that use data from Hudson Bay to try to fit the logical terra to the data. So it's actually using like real data sets and trying to fit the neural D to that. And if you go, I hope that after the workshop you can read through the code, and you're gonna be able to understand most of it, and actually see that it's not very different from what we tried today, except that instead of using fake data, they're using actual data. And then finally, we can mix both dynamics with the stochastic systems. So you have stochastic differential equations, so SOTEs or STEs. There's different, they can come with or without the O, but they're actually the same thing. And also the stochastic partial differential equations, to mix partial differential equations with stochastic processes. And in many cases, you just modeling like random processes that change in time. So if you're familiar with the Brownian motion, so Brownian motion is an example of a stochastic process. And so like it basically describes how particle changes in a field under the constraint under around the walk. And it can describe this using a mix of dynamic systems and stochastic process. And then another point of entry is, of course, the SciML page. It contains a lot of the component feature for this field, like it contains the description of different packages, where you can find help, where you can find documentation, everything. So and then finally, there's some reference here if you wanna read some of the papers related. So without further ado, I'd like to thank you for your presence and participation today. I hope that you enjoyed the workshop, and maybe open the floor for any final comments or questions that you might have. Otherwise, we can call it a day. Okay, so practical applications. So there's a lot of practical applications. So in the paper that I mentioned, the Universal Differential, like they mentioned a lot of different cases. So one case would be like to fix this data set, the Hudson Bay company data to the logical Volterra. So you wanna try to explain the dynamics that you observe in the data using like systematic differential equations. So you would use a neural network. Another example would be like so in like drug discovery, like if you're trying to find like the mechanisms inside of the cells that drive like the dynamics of a drug, then you're looking into differential equations. And so here in the SciML page, there's actually like a lot of like applications. Is climate modeling, quantum optics, robotics. So just go through the news, and you find a lot of like different applications. So also for like COVID modeling, that's where I got that's how I got involved, is through modeling infections. So yeah, so there's a lot of applications in different fields of science. Yeah. Yeah, so I agree with you. Yeah, in the field of physics also they've been using a lot of this toolkits to fix more and more complex data sets. So I guess I would say it's a way of framing problems. If you think about if you come out with some data set that looks like time series, you could consider framing that problem in terms of differential equations and see if you could fit this framework. Yeah, you're welcome, and you're free to stay in contact via email. I think some of us have been working with Julia a lot, and also with the ODUs. So if there's something that you would like to learn more, or if you just want to touch base with us offline, then just write me an email, and then we can continue a conversation. Yeah. So thank you, and I'll call it a day then. See you.